In this video, we're going to look at estimating sample size. Now, when we look at sample size, there's several things we need to consider. The effect size that we want to find out, the alpha error, and the power. And if we're doing a randomized controlled trial where we're going to use analysis of covariance, and we're going to have an initial baseline value as well as a follow-up value, then we also need to know the correlation between the baseline and follow-up. So let's first consider effect size. So we look over here, we have various effect sizes. Now remember, effect sizes are in standard deviation units. Now, one of the things you just need to do is consider your variable that you're interested in, and look in the literature and see what differences people have found before. So, is there a difference like half standard deviation, full standard deviation, more than that? I think you don't want to really be paying a lot of attention to studies that have only seen something that's less than a half standard deviation. It's not that they still can't be scientifically relevant if they're greater than 0.2. It's just that you'll need so many subjects you won't be able to do it in a master's thesis time frame. So look and kind of determine your effect size, or determine your the difference between groups in standard deviations. Now, if you're going to do a crossover design, you can do the one on the other, this one over on the second page. But we're going to just focus on this table. Now, let's say. So we come down here, we see 0.2 is kind of the minimally scientifically relevant. This is kind of our minimum clinical relevance. Now, you want to give yourself some room. Usually 0.5 is kind of a very minimum, but really if you've seen your previous research and you've picked a topic that looks like it might be reasonable for 0.8. Or if you've looked at the standard deviation of your dependent variable and you said, oh, 0.8 standard deviation effect, you interpreted or converted that to the actual units of measurement, you say, well, really, I want stuff to be at least 0.8. Then you can use that, or even 0.6. Now, you have to think, and this is kind of a funny thing, but, well, not really. Just think about what you can realistically do in the time that you have available to you. And how many subjects can you run? And then that's going to depend a lot on what your sample size is. The other thing is, in this case, we're looking at measuring a baseline and then follow-up. Now, with any luck, you'll have some information from previous papers that look at the correlation between pre and post studies, and you can get an idea. If I don't know the correlation, then what I'll say is, well, a correlation of 0.7 is pretty good, because when you square that, you get 49, or about 50% of the variance is accounted for in that correlation. So I tend to use 0.7. Now, sometimes when you do it, they'll be correlate a little more, sometimes a little less. So that's just a starting point. Now let's look at our table and see what we have in our table. We have over here the correlations. We have a section where the alpha is 0.05, power is 0.8. Alpha is 0.05, power is 0.9. Alpha is 0.05 and the power is 0.05, or power is 0.95. Then I've got an alpha 0.01, a power 0.9. You know, it just, and you can change, if you want something other than these, you can change a section by changing the power that is up there, because what that's going to do, this cell right here, the power of 0.8, is going to change this cell, which is using the formula, the same way this value is going to be used to go there. So you just change these values and you can do it. You can also, if you want to, for some reason, do 0.32, you could just write in 0.32 and everything would be updated. So power is the probability of correctly rejecting the null hypothesis. Alpha is the probability of incorrectly accepting or rejecting. Alpha is the probability of incorrectly rejecting the null. Power is the probability of correctly rejecting the null. Okay, hope I said it right that time. All right, let's get our thing up a little bit bigger. Let's just do a half standard deviation. We'll just do a simple one. So this is an example of two proportions. If you had a proportion, the x1 is standardized at 0.5, and let's say the number of people that score positive on your test, then the number of people that in one group, or the number of people that were successfully treated. Let's go that way. Half the group were successfully treated, 31% were successfully treated in the other group, an odds ratio of 1.62. That's an equivalent way on using proportions to a standard deviation change of 0.5 standard deviation difference between two group means. Now, if you did not have analysis of covariance, you would use the values in here. And so what you would do is say, well, how many subjects are reasonable for me to gather? I might say I could, and this is per group, so I might be able to do 20 per group. Okay, well, we look up and down here. We don't really see anything. That numbers just get bigger as we go out. So 19. If you weren't doing analysis of covariance, if you didn't have a baseline, you would probably have to expect a minimum, or you'd be able to detect a minimum of standard effect size of 0.9 standard deviations. So that's a pretty good size difference, and you would do it. But if you add a, and that's at a power of 0.8 and alpha 0.05. If you wanted to go to a power of 0.9, you would need 19 per group. Now, generally speaking, we're going to always try and have a baseline test. Most of your situations, you'll be able to start with something and then move on. So your correlation is going, and so we had mentioned, here's your row of correlations. So you could be correlated 0.1 between baseline and follow-up, 0.3, 0.5, 0.7, 8, 9. So we're going to go with 0.7, and if 20 per group, that gives us right here. So we could have an effect size of 0.65 with 20 per group with a power of 0.8. Now, power of 0.8 is a 20% chance of not finding a significant difference. That's kind of high, I think. So you might want to come over here, and what is your 0.7? You could find an effect size of 0.75. Okay, that's, not too bad. Not too bad. At a correlation of 0.7, power of 0.9 alpha, 0.05. We always use alpha 0.05 for purposes of sample size estimation. Though a time when it would be less appropriate is if you had, maybe you had 5 treatments or 3 treatments, and you wanted to do a little bit of control for multiple comparisons. Then you could reduce this alpha to 0.01. Let's see what happens when we reduce our alpha. And I'm going to change this to 0.99. Now, where were we? We were at 19. That is a point. No, nope, over here. 19, a 0.75 effect size. Well, I think it just did it. We went from 19 to 24. So it took a few more to adjust for multiple comparisons. All right. That's basically all there is to it. You figure out your effect size, you figure out the reasonableness of your sample size, you go searching for something to get in that neighborhood. You can go across, or you can just say, well, I have 20 per group. What's the effect size I can detect? And see if that's reasonable. You kind of iterate between things. It's all subjective. And it's just a matter of coming up with seems like a reasonable difference for to get a scientifically meaningful study. You want your effect size to be the biggest it can be, power the strongest it can be, but realizing that it gets tough. You are under restrictions. And it may be you come up with a study that you can only run so many subjects, and the effect size just has to be unrealistically big, and you can't do it. So that's how that works.